Welcome, everyone. My name is Ali. I'm very excited to be here and to present our work. Today, I will talk about our paper, Adversarial Training of Power Systems Against Denial of Service Attacks. This is going to be the layout for my presentation. As for introduction, Department of Energy of United States projected that the power systems in the United States will integrate smart grid technologies by 2030 all over the country. And the main reason for this ambition is that smart energy grid networks offer a lot of advantages, such as distribution of electrical energy from the providers to the customers in an optimal way using communication technologies. And because the basic core of SEG is the telecommunication network, the power systems which were previously isolated are now more than open and accessible to general public. Of course, this makes SEGs open to the cyber physical attacks as well. Our motivation is driven by the following observations and facts. For example, power systems have quality requirements, and for this reason, operators monitor and analyze disturbances with the help of SCADA systems. And those operators try to identify and correct the issues, such as faults or attacks, constantly. The problem is when the system gets large, when there are a lot of sensor arrays, then the data coming from the sensors can be multidimensional, and human operator may not be able to detect abnormal events that easily anymore. So to overcome the human limitation, modern SCADA systems offer a platform for discriminating power system disturbances using machine learning tools. But it is also a known fact that with enough high informational input, machine learning systems can be deceived, and this is our starting point for this study. So in this work, we analyze the vulnerabilities of disturbance classification systems, and specifically we look at denial of service attacks where we target some sensors. And by making the sensor data inaccessible, we can basically make that feature unavailable for the machine learning algorithm. Then our hypothesis is, by finding and deleting specific sensor readings or features, we can cause classifier to mispredict a label. And by deceiving classifiers, we can disguise abnormal events or even more complex attacks as just normal regular events. Then our objective is, we want to develop a denial of service attack to deceive neural network-based classifiers, and we want to defend against such denial of service attacks as well. Before we move forward, I'm going to make some set of assumptions to meet our objectives. For starters, we assume a white box attack. That means the adversary has access to the control system and the sensor reading. And then we assume the adversary has a limited budget, meaning that it can attack only a limited number of sensors. Within the control system, there is an attack detection mechanism utilizing a machine learning model. This model is assumed to be densely connected neural network with ReLU activations. And the model can label events as normal and abnormal. So due to the white box attack assumption, the adversary has access to the weights of the model as well. And we assume that adversary attacks only at to the events that are labeled as abnormal. And lastly, we assume that neither data or the attack is time correlated. In other words, the DOS attack deals with each measurement individually. Suppose that we have effects which can classify sensor measurements. It's our neural network. It takes an xi as an input. I here is the ith instant measurement instance. Each feature of the input data corresponds to a sensor reading, and the neural network is expected to predict the label for a given instance as -1 for being a normal event, or +1 for being an abnormal event. Compared to gradient-based attacks, which impose only small changes to the data, to the input data, here we determine what features we need to delete. So for that purpose, we define a vector alpha, which describes what features needs to be deleted. And when, for example, Jade feature in the input data should be attacked or deleted, then that particular element of alpha is going to be equal to 1. So 1 means the feature is going to be deleted, 0 means it stays there. Then the attack model can be formulated as a maximization problem, as you can see here. Aim of this optimization problem is finding an alpha such that we should be able to switch the predicted class from abnormal to normal label for a given input. In other words, the objective of this function is finding features to delete, which is going to cause misprediction. Here we use the hinge error between the true and predicted label. And the optimization, if the optimization fails to maximize this error, the alpha is going to be a vector of zeros, meaning that there are no features to delete. And of course, attacker has a budget, and it is denoted as K here as a constraint. For linear classifiers, this optimization problem given here, it's a convex mixed integer linear programming problem. So it is a MILP. While MILP is an NP-hard problem, it can be solved still efficiently using heuristic methods. However, for neural networks with nonlinear activation functions, the solution space is not convex anymore, and the optimization problem cannot be written as a MILP anymore. A solution could be still found by applying computationally exhaustive nonlinear programming approaches. However, it's going to take some time, and you cannot guarantee you will find the optimal solution for that problem. Here, we can consider some relaxations and assumptions regarding the neural network structure to find a solution faster than NILP does. We are focusing on neural network with ReLUs because they hold a piecewise linearity characteristic. Therefore, it is possible to reconstruct a neural network as a set of logic formulas using disjunctive normal form. As a result of that, we can solve the problem using MILP method. So as an example to how we can do that, suppose we have a neural network with a single ReLU activated neuron. We omit the bias term for the presentation purposes here. And we describe the neural network as you see on the left side. Each formula in the DNF clauses correspond to the state whether a ReLU is activated or not. And using these clauses, we can write the maximization problem, the attack problem, as an MILP problem. And each clause can be regarded as a collection of constraints that needs to be satisfied based on the state of the activation, whether it is active or not. Here on the right side, we give the MILP for the first DNF clause, and note that how the first clause is matching with the constraints of the MILP problem. So for each clause, we can find alpha that will maximize the error. Eventually, for a system that has k number of clauses, we can determine alpha max that will maximize the prediction error. There are some limitations regarding that, though. For neural networks with k neurons, there will be 2 to the power of k clauses. So each ReLU can be active or inactive, and all of the activation states for each neuron is independent of each other. And to find an optimal solution, we need to go through all of these clauses and compute the alpha. And for large networks, this search is extremely exhaustive and infeasible as the number of clauses is growing exponentially. So instead, we can go through each clause until we find a solution that will cause the misprediction. So it's a relaxation. In other words, we don't need to maximize the error among all of the clauses. Instead, we only need to find one clause that will cause the mislabeling. So once we satisfy the misprediction, we finish and we go for the next data instance. Here, the algorithm outlines the idea of the proposed attack model. Given this algorithm, in the worst case, the approach will go through all of the clauses if the problem is not feasible. And most of the time, the problem is feasible. And if the problem is feasible, the solution is usually found when all the values are activated. Again, in the worst case, we are comparing the exponential complexity for the proposed attack model to the factorial complexity that is, we must go through all of the feature combinations to delete. So for large dimensions, factorial complexity is definitely much worse than exponential complexity. But we could go further with relaxations. We could go around the worst case scenario by limiting the number of clauses to solve, because we observed that when the number of activator values decrease, it is getting harder and harder to find a solution. So that's something we can consider, but we didn't apply this relaxation for our problem. So let's talk about the defense model. Usually, the simplest solution to defend against adversarial feature deletion will be training the classifier using adversarial examples. And accordingly, we can write the defense model as a minimax problem. Here, our aim is finding the weights that will minimize the average maximum prediction error caused by adversarial examples. One training strategy that we looked into is one-shot training, where we train a neural network with a data set, which is going to be the baseline neural network. Then we compute the alpha for each examples with the given baseline and try the adversarial example data set. Finally, we train a new network, which is going to be our robust resilient network, using the adversarial example dataset as the input training dataset for that specific model. So let's go to the evaluation. For the evaluation, we use the dataset specifically generated to investigate machine learning algorithms for power system disturbance and cyber attack discrimination. So the network we used for the evaluation has phasers, breakers, switches, etc., and each of those components are monitored through several sensors. The original data set contains a variety of scenarios categorized under normal and abnormal events. There are 128 features for each measurement instance. Each feature corresponds to a sensor. The data set we used contains 5,000 events. We used 80% of these events for training and the remaining for the testing. And the ratio of the normal events to abnormal events is about 28%. So this evaluation uses a single hidden layer neural network to discriminate against abnormal events and normal events. Our baseline model has 5 neurons in the hidden layer, and ReLU is used as the activation function. The aim of the model is detecting whether an example is normal and abnormal. So because we have 5 ReLU neurons, this yields 32 clauses to go through for each example. And the MIL problem for each clause can be, we formulated the MIL problem for each clause using CVX-Pi and Grob optimizers in Python. We focused on a variety of attack budgets corresponding to small fractions of features. So when we trained our network, the baseline model that we have had above 80% accuracy both for training and testing data. So the values are similar and we can say the generalization is okay. However, when we attack to the baseline model, the prediction accuracy drops significantly for each budget. And it decreases even further when the budget of the adversary increases. So for the given baseline, we can safely say that the attack is very efficient. For the defense, we generated the adversarial training data set by attacking the baseline with the given budgets. Then we trained the resilient model using this adversarial training data set. We also checked how well the resilient model is generalizing over the original data sets. And finally, we attacked the defense model. As you see, the defense model generalizes well over the original data set. And when the resilient model is attacked, then the accuracy is dropped again. However, when compared to the baseline model, we can see some improvements for each of the budgets. So we can say that while the defense model works, the improvements are limited, but still there are some improvements compared to not doing anything. So, summary. The aim of the study is deceiving machine learning-based detection systems using denial of service type of attacks. And we showed that by making specific sensor readings unavailable, we can craft some very powerful attacks and hide abnormal events. We also demonstrated that by writing a neural network with ReLUs as a set of MILPs, we can find features to delete and cause mislabeling effectively. Lastly, we showed that a defense mechanism could improve the robustness of the network. However, the improvement may be limited. Because of that, as future research, our top priority is finding more reliable defense models to increase the accuracies against attacks. This study was focusing on 2 categories. We want to see if the attack mechanism is adaptable to deceive multiple category systems. We assume white box attack model. We want to study how transferable the attacks are for unknown models. So in other words, a black box model approach is something we want to look into. And lastly, we assume the network is densely connected. We are curious if it is possible to devise attack model for convolutional networks. I want to acknowledge Science and Security Program for supporting my research. I also want to appreciate IBM for providing graduate fellowship. And thanks for your time and interest. I will be happy to receive your questions now.